let's get on to the interesting stuff. PAT. What is PAT and why is it useful? So you may or may not know, but we're actually in the middle of the fourth industrial revolution. So there was the first industrial revolution that has the name the Industrial Revolution. It's the most famous one, late 18th century, and it was mechanization. It was when people started to be able to use equipment and machines to do the job that people used to do. And it effectively came about from the steam engine. The steam engine became efficient. James Watt actually made a way of making it efficient using condensers, and that kickstarted the whole industrial revolution. Then a bit later, in the late 19th, early to mid 20th century, came along the second industrial revolution, and this was mass production. These are things like Henry Ford building automobiles with a production line. Electricity allowed the division of labor. It was a way of improving efficiencies that had come about from the original industrial revolution. Then at the back end of the second half of the second 20th century, we had the third industrial revolution. They decided at this point to call it the digital revolution. And this is automation, electronics, and IT. This is effectively the silicon chip enabling digital processing and computers to take a much more leading role. And we are now in what's been given the sexy name of Industry 4.0, and this is the fourth industrial revolution. And this is going beyond just computers. This is computers talking to other computers, talking to equipment, the robotization, cyber physical systems, and digitalization. This is the beginning of fully automated processes. An example that I come across quite a lot is an oil rig with no people running it. So the unmanned oil rig, something that can sit out in the middle of the ocean, and it can take crude oil from the sea, get it to the point where it can go down a pipeline or into a tanker for refining later on, with absolutely no human involvement. The plant, or in this case, the oil rig, has sensors that talk to each other, and it just knows what to do. Now, we're actually quite a long way away from that, but that is where people want to get to. And that's what we're living through at the moment. To do that and to enable cyber physical systems that interface with reality and talk to each other and make decisions, we need sensors. And you need to be able to understand what your process is actually doing. Broadly speaking, there are three types of analytical measurements. There are simple online measurements. We tend to call these parametric. They're things like pH probes, temperature probes, oxygen levels, turbidity measurements, optical density measurements. So they're very simple. They measure one thing, but they do it all the time. And then at the other extreme end of that, we have things that are offline measurements, such as high performance liquid chromatography, chemical assays. These can directly monitor concentrations and give you really meaningful information, but they're very slow. You need to take a sample offline. It's difficult to automate that, and they can be very expensive. Then in the middle, we have spectroscopic measurements. And I'm going to go into spectroscopy in a bit more detail later, but that's kind of halfway between the two. Spectroscopic measurements do look at the chemicals that are present, and they do it in real time, but they don't give as much information or the precision of information that some of the offline measurements can give. So let's look a little bit into some of those simple online measurements in a bit more detail and understand what those are. There's quite a lot of them. This is not an exhaustive list, but these are ones that we come across quite a lot and that customers tend to have installed on their processes already. So at the left, we've got capacitive measurements. These are things like electrical sensors that actually sit in the process. They're very good for biotech, where you're trying to look at things like cell growth, but not so good for oil processing. Refractometers, they can be quite good. They tend to be single wavelength of light, and they look at the refractive index of a process. So if you're trying to look at one thing and one thing only, for example, water dissolved in edible oils, that could be done with a refractometer. But your process needs to sit at an exact temperature because the refractive index of that mixture will be changed by the amount of water present, but it will also be changed by the temperature. And you can't tell whether it's the temperature or the water that's causing that change in refractive index. So if you've got very tight control and you know that you've got a complete control over temperature, that's a really good type of measurement. If you don't have control, these measurements start to fall over. Optical density does something similar. That can be linked to something like a colorimeter that looks for color. So if you're trying to look at the color of your process, that kind of measurement could be done in a similar way. Temperature probes. We've all used temperature probes. We've all used a thermometer ever since we were a tiny child. I suspect somebody has at some point taken your temperature. There are loads of different types of temperature probes. You can have the traditional old school mercury-based ones going right the way up to infrared light-based ones that work off reflectance and everything in between. I think we all know how those can be used. pH probes, you might want to measure the pH. These work very well in aqueous media, but in non-aqueous media, pH isn't terribly easy to measure. So for example, free fatty acid concentration by pH is probably very difficult, if not impossible. Dissolved oxygen probes, they're very good for things like biotech, where you're trying to, if you've got an aerobic process, you're trying to pump as much oxygen in that as possible. But for things like edible oils, they're less helpful. Ion-specific electrodes, again, work very well with aqueous methods where certain ions can dissolve when they're mobile. So for example, looking at things like calcium or magnesium ions can be done with ion-specific electrodes, but only in aqueous phase. So if you were to take an oil and wash it with water, you might be able to extract certain ions into that and then detect them, but that kind of becomes an offline measurement at that point and not truly online. And lastly, you've got molecule-specific sensors. A really common one of these is glucose. Anyone that knows anyone with diabetes will have seen these, where you can take a drop of blood, put it on a glucose level stick. That works with an immobilized enzyme. I believe it's horseradish peroxidase that looks at the amount of glucose present and gives you it actually gives you a current and a voltage, and that tells you how much glucose is present. So there's a huge variety of different online measurements, but none of these really give you the information that would allow online control of things like seed oil refining. And then at the other end of that, we've got the offline and extractive measurements. And these, broadly speaking, fall into three categories. We've got the chemical and biochemical assays, we've got direct instrumentation measurements, and then chromatographic techniques. So the chemical and biochemical assays, these fall into things like titrations. Free fatty acid titrations, for example, are quite commonplace. And chemical reactions. There is a fantastic book that some of you may have come across by Vogel that lists every single chemical assay around, but there are lots of them. It's not light reading, but there are absolutely hundreds of different chemical reactions that can be done for quantitative and qualitative analytical chemistry, but they're all very slow, very expensive, and they require skilled technicians. They're not trivial. The direct instrumentation, things like nuclear magnetic resonance, and I've just spotted my deliberate mistake, that should say ICP, not IPC, AES and AAS, these actually do take direct measurements of chemical concentrations, but again, these require skilled technicians to run, and they often need dilution and reference standards as well. And then at the other end, we have chromatographic techniques, things like HPLC, LCMS, GCMS. These all need, the MS stands for mass spectrometry, and those actually are effectively the detector. But HPLC needs to be bolted onto a detector. It is effectively a posh sieve. And a sieve is great, but you do need something at the other end to do something with what's been separated. And they almost always need dilution. And you've got to take the samples offline. You've got to go and actually extract them at some point. And we've tend to notice, we're working with customers and clients, that samples taken at around about this time of day are normally quite trustworthy. Samples taken at 2 a.m., less so. And that's simply because people get tired. It happens. So these techniques are very powerful, but they all have drawbacks. So we've either at one end got the simple online measurements that don't really give you the information you need to make a change, and offline measurements that can't be done quickly enough to make a change. And this is where spectroscopy comes in.